talk about vapor pressure. We've been talking about boiling and evaporating, and what's the difference? So, vapor pressure happens without any heating other than what the room or whatever the system, the area, the surroundings is providing. And things in the liquid phase are leaving the liquid phase and going to the gas phase. And after, if you plug that up in some closed system, there'd be some pressure that builds up. So these particles would be bouncing around and causing a pressure, and that is the vapor pressure. So your vapor pressure is what happens as a result of things hitting the walls as a gas phase. So the difference between evaporation and boiling is in the case of evaporation, things are leaving in a sort of, molecules or atoms of some liquid are on or near the surface and in the right direction, moving with enough speed to break away from the liquid phase. That's evaporation. The key here is that the atmospheric pressure is higher than whatever vapor pressure forms. If the vapor pressure, however, is equal to the atmospheric pressure. So what's pushing it down is equal to what is getting pushed back up. Then that is when boiling occurs and you start seeing those bubbles. So to visualize this a little more, we talk about this phase diagram. This phase diagram represents the three phases of matter for any substance. So this chart will be available for any substance. I believe this one is not water. And I know it's not water because here. We'll talk about that in a second. But anyway, um, at low temperatures, okay, and high pressure, so you're pushing things very close together and they don't have a lot of movement. Hopefully, you can imagine that that's where solids exist, because if you think about where solids would exist, solids that have very little temperature moving them around and very high pressure pushing them together, that would be when the particles are compacted into a solid. When you have very high temperatures, so the particles have lots of energy, and very low pressure, so plenty of space for them to spread around, that hopefully makes sense that this is the gas area. So everything in this little area here is where that substance would be a gas. Everything in this little area here is where that substance would be a solid. And guess what happens between solid and gas? You have liquid. So in that area in between is where liquid happens. Okay, so if that's true, then this line here, I'll change its color so you know which line I'm talking about. This line here represents the line between solid and liquid. So that's where it's melting or boiling. And if this point is at 100 degrees at 1 atmosphere, then that is not water. Water does not melt at 100 degrees Celsius. It boils. So that should be over here if this was water. So this is the phase diagram for something other than water. All right, so here it is for water. Um, as we were just saying, this 1 atmospheric pressure is considered normal because that's what the atmospheric pressure is on um, Earth at sea level. So we call that normal pressure is 1 atmosphere. So the normal freezing point for this substance would be the point where at one, the solid, and remember this area is the solid, this area is the liquid, and this area is the gas. So where solid becomes liquid at 1 atmosphere is considered the normal melting and freezing point. So that is 0 degrees Celsius for water. The normal boiling point still at 1 atmosphere, where things change from liquid to gas. So that would represent that point, and that is 100 degrees Celsius. So at 100 degrees Celsius is where the normal boiling point. The triple point, now this I'll get into a little bit, is where all three things exist at the same time. Okay. So the triple point is this point A, where where everything would exist at the same time. You may have been to a state where there's a border where you can put your foot in three states at the same time or something, or five states or whatever. That's basically what this is. Three states happen at the same time. I'll show you that in a second. Then there's also the critical point, this point E, which I don't really quite understand why we get into this. But anyway, that's the point beyond which only gas can exist. It's a point of no return for gas. All right, so that's all that. Let's take a look at a triple point here. So this is cyclohexane. Cyclohexane is a liquid here. It's being pumped on, and then you can see as they pump on it, it's becoming a solid. So they're reducing the pressure by removing the atmosphere. And then you will see that solid will melt into a liquid and boil into a gas all at the sort of the same time. And that's sort of the triple point of cyclohexane. So there you see it's boiling. So you got the gas and liquid, and then it goes back to a solid, and then it starts boiling a little bit. So that's the triple point that we're talking about here. So moving on. So boiling is what happens when there's enough heat energy provided to the liquid that the particles can create enough vapor pressure to counteract what air pressure is pushing down on it and allow gas molecules to escape as a gas. And that's when bubbles start forming. That's the difference between boiling and evaporation. Think about if you think about the column of air above us, right? Here we are on Earth down here, and here's the end of the atmosphere up here. So as you move down in that atmosphere, you get more and more atmosphere above you. There's more concentrated molecules of oxygen and nitrogen and whatnot in the air that are above you. And that's causing greater atmospheric pressure to push down on the water. And so as a result of that, at sea level, you can boil water at 100 degrees Celsius because that's how much energy is required for that water to counteract all the pressure of the air. As you move up, though, you can see the temperature goes down because it doesn't have to fight as hard at, say, this point because there's not as much concentrated atmosphere pushing down against it. So the atmosphere pushing against the boiling process is not as extreme the higher up in the atmosphere you go. So that's why it doesn't take as much energy to boil water in higher elevations than it does at sea level. Okay, so taking that another way, I was able to evaporate water at room temperature um, by basically putting a vacuum on it. So if I put a vacuum on water by removing that atmospheric pressure by taking away these things, and I talked about this on my in one of our labs, right? If I take all this away, then there's nothing fighting against the water from leaving, and you can boil water at room temperature. All right. So using the states of matter FET, if we want to go from a solid to a liquid, we need to give energy to the particles. And if we want to go from a liquid to a gas, we need to give energy to the particles. So those things are endothermic, right? So endothermic that way. It's exothermic to go backwards. Turning a gas into a liquid, we have to pull energy out. And hopefully this all makes sense to you because, right, when we pull energy out, when we cool something off, we're pulling the energy out of those molecules or particles. So they have to slow down. And when they slow down, they can form the solids and liquids that we want them to because they don't have the energy to leave. To turn a gas into a liquid or a liquid into a solid, that's exothermic. We got to pull energy out, right? Pull out energy to go this way, and we got to put in energy to go the other way. All right. So why am I bringing that up? Because it turns out delta H fusion and delta H vaporization are the reason why your air conditioner works. So let's talk about what happens here. We have a refrigerant, and that refrigerant goes from the liquid phase to the gas phase inside the house. So this is in the house right here. Um, in the house, we turn a liquid into a gas. And if we turn a liquid into a gas, it needs energy and it pulls the energy out of the room. So from the room, little heat energy blocks are leaving the room and going into this coil to allow the um, refrigerant to turn from a liquid to a gas. Then it gets pushed into a compressor and it gets pushed down. So we're going to increase our pressure. And so the liquid became a gas, and then we're going to move it up so it becomes a liquid again. So in the process of doing that, in the process of turning a liquid into a gas back into a liquid, we have to release the delta H vaporization, and that's what happens outside where the fan is. So now we're releasing the energy boxes that we put in the house. So the energy boxes went in to the refrigerant in the house to turn it from a liquid to a gas using delta H vaporization. And then outside of the house, they got compressed back from a gas into a liquid, and the energy was released using the fan outside. And so that's how any refrigerant works, including your refrigerator.